everyone, so today we're going to be looking at the Beckman rearrangement and the Schmidt reaction. So first we're going to start off with the Beckman rearrangement. In this example we have a nitrogen double bonded to a carbon and we form an amide, which is formed in all Beckman rearrangements. This is done with a bronzed or lewid acid, and in our mechanism example we are going to be using OH as our X group. So we start off with with an oxime, which is this functional group right here, and we're going to protonate the OH to form it into a good leaving group. So now that we have our OH and a good leaving group, it is time to do an alkyl rearrangement. So we're going to take this bond with the carbon and R1 and move it to the nitrogen over here, bond it with the lone pairs. And at the same time, we are going to kick off this water, which leaves us with this structure. And we can do a resonance form with this lone pair on the nitrogen and make a triple bond to have the nitrogen hold the positive charge, so the carbocation, to create a major resonance form. But for this example, I'm going to show in the mechanism, the minor form shows what actually is happening chemically and structurally, I guess, yeah, electronically is a better word. So we're going to take the water that we just removed and attack it with this to the carbocation. So now that we have our water attached to this carbon, it is time to deprotonate the water. So we're going to use a base and deprotonate like this and put the lone pairs on the water. And now it is time for tautomerization, which is a word we should all be familiar with from Orgo 1 and Orgo 2. And this is basically just a structural rearrangement of the molecule. So first, we are going to start off by bringing down the electrons to form a carbonyl, as we see in the product, and then we are going to protonate the double bond. This leaves us with a protonated carbonyl and then a single NH bond. So just to remove this, it's quite simple. We'll deprotonate like so, and we are left with an amide. Okay. So the next reaction we're going to be doing is the Schmidt reaction. And this is the formation, results in a formation of an amine, an amide, or a nitrile. And we have three key functional groups that are used in this reaction, and those are the carboxylic acid functional group, a ketone, and an aldehyde. So in this example, we have the carboxylic acid, and using a key reagent known as hydrozoic acid, and then this is acid catalyzed to form an amine. In this example, we have a ketone, which also uses a hydrozoic acid and a Lewis acid to form an amide, and then the aldehyde example, again, hydrozoic acid to form a nitrile group. So in this example mechanism, I'm going to be using the ketone because it's pretty similar to the Beckman rearrangement and allows for easy comparison. So the first thing we're going to do again, because it is in acidic conditions, is protonate the carbonyl. Now that that's protonated, we are going to use this hydrozoic acid to add to the carbonyl, to attack the carbonyl. So we're going to just go like this, there, and then kick those electrons up to break that bond. And now we have a lone pair, which is right there, and now this hydrozoic acid is bonded to form this tetrahedral intermediate. Now that we have our tetrahedral intermediate, we're going to deprotonate this hydrozoic acid. So we're going to go like that, and then put the electrons between the nitrogen and hydrogen bond back onto the nitrogen to give us a minus charge on the nitrogen and two lone pairs, which will be used in a minute. But first, we want to make the OH group into a good leaving group by making it water. So we're going to protonate the hydrogen. And now we have water as our good leaving group. So we're going to kick this off. But we're also going to use the lone pairs on this positively charged nitrogen to form a double bond with this carbon right here. So now that we have this double bonded nitrogen to the carbon, we can do our rearrangement. So we're just going to take this out, we're going to do an alkyl rearrangement. So we're going to take this group right here, the R1 bond, and shift it up to this lone pair nitrogen, and at the same time we're going to break the bond between the two nitrogens. So now we get the resulting two structures, our resonance structures. This is the major structure as in the other one, which has the positive charge on the nitrogen. But to show the electronics of the reaction, we have our carbocation intermediate, and we're going to have our water that we kicked off come and attack this carbon, which leaves us with a positively charged water group and a double bonded nitrogen. And again, we want our amide as our product, so to do this, we're going to have to do a tautomerization. But first, we're going to deprotonate this hydrogen and put the electrons onto the oxygen. Then, we are going to use the lone pair that's on the oxygen and bring it down to form a double bond and make a carbonyl, a positively charged carbonyl, and then we're going to protonate this double bonded nitrogen to give us the same thing as we did in the other tautomerization, and again, just deprotonate, and we get our amide. So now I'm going to show you a couple examples that can be found in the literature. An example for the Beckman rearrangement is we have a cyclohexanone oxime, and this one results in a ring expansion. So we go from a 6-membered ring to a 7-membered ring, and we use H2O. This example, they were trying to do it without a catalyst, but again, a Bronson-Lewis or Lewis acid works for a Beckman rearrangement. In the Schmidt rearrangement, we have an 8-membered ring that expands to a 9-member ring, and again, we have our hydrozoic acid as the key reagent for the Schmidt reaction. So those are our two reactions, and I hope you enjoyed. Thank you.